class 12th. In the last lecture, we have completed the lens maker formula. Today, we will talk about on how many factors the focal length of a lens depends, and the 6 cases of image formation using convex, 2 cases for concave, and the last linear magnification. Starting with the first topic, the dependency of focal length on the some factors. And for start, see, this was the last equation when we left the last session. So the focal length means in this equation the f is in denominator. So the quantity, the factor which is in denominator will be directly proportional to the focal length, and that will be in numerator inversely proportional. So in denominator there is only radius of curvature. So you can say the focal length is directly proportional to the radius of curvature and inversely proportional to the refractive index of the medium. Suppose the lens is of glass. So as you are increasing the refractive index of glass, so the focal length will decrease as they are inversely proportional. And the same way, as you are increasing the radius of curvature, the focal length will increase. Friends, I will show you in detail. But suppose this lens, I have explained you that the focal length of the lens depends on the refractive index of the medium. Suppose this lens is placed in any medium. Now this lens is not a single medium. There are 2 media. Suppose in a bucket there is liquid. You can take water, and I am placing the lens inside that. Now what will happen to that focal length of the lens? First of all, I am talking about the focal length is directly proportional to refractive index. See in the equation.
So let's see the factors on which the focal length of a lens depends. So talking for the first on refractive index. As I have explained that focal length is inversely proportional to the refractive index. So let's write one equation. See this equation, the lens is placed in air. So the focal length equation 1 upon Fa by the lens maker formula, the refractive index of glass minus 1 and R1 R2, the 2 radius of curvatures. Lens is now placed inside a water. Then what will be the new equation? Now see the focal length of the lens in liquid. So light goes from liquid to glass, Lng minus 1 upon R1 minus 1 upon R2. So we have to compare these focal lengths. For that we must know this value, because this is not with respect to air. This one is there with respect to air, but this one not. So I am writing that first. So to find the approximate value of Lng, we can see this. So for example, to calculate this value, let Ang is 1.5 and Al as water is 1.33. Then what will this? I am just considering, this is not sure, I am not exactly there saying that Ang means only this. So I am just taking example that let the glass has refractive index 1.5 and the liquid has refractive index 1.33. Then what will happen? That is nearly 1.12. Means you can say Lng is around 1 point something, while Ang is more than that. See here, Ang is more than that. So we can see here as 1.12 is less than 1.5. Same way Lng will be less than Ang. So this value is less than this value. So let's divide this. On dividing 1 upon Fa upon 1 upon Fl, this value will come. 1 upon R1 minus 1 upon R2 will be cancelled because length is still same, so radii of curvature will, on further solving you will have this. The Fl will go up, Fa will come down. Fl upon Fa is Ang minus 1 only and Lng minus 1. So you know that this value is less than this value. So this value is less. So the minus 1 will give little more. And this value is more. So Fa will be, after doing minus 1 will be less. Or you can say this is greater value, this is lesser value. The ratio will be same. So this will be greater length, this will be having lesser length. So you can say Fl is greater than Fa. So what you found? That whenever the lens will placed inside a liquid, the focal length of that lens will increase. But remember this, nature will remain same, but the nature of the lens will remain same. Nature means the type of lens. If it is converging, so this will remain converging, or if it is diverging, then it will remain always diverging type of.
So you have seen that focal length of the lens depends on the refractive index of the glass of the medium, and if the glass or the lens is placed in any liquid, then at that time the focal length increases. But remember this, the medium in which it is being placed that was having the less refractive index than the glass one. And suppose I am placing that glass, means the lens, means you can say that glass is having refractive index 1.5. I am placing that glass in such a medium, in such a liquid which has the same refractive index of the glass, means the lens is being placed inside a liquid. Lens and the liquid both are having the same refractive index. Then what will happen at that time?
To understand that, consider this lens has any refractive index, let n, and a container has some liquid whose refractive index is also n. As I said, both are having the same refractive index. So on placing this lens inside here, if both are having same refractive index, so I'm showing you, this is the lens. Are you able to see? So it means when the medium and the material both are having the same refractive index, so the lens will become invisible inside. So we have to prove it. Let's prove it first. First of all, considering both are having different refractive indices, then we are having this equation when the lens is placed inside liquid. The above equation can be written as further. On doing LCM here, you can see this is the equation, final equation. Now I'm considering this glass and this liquid both are having same refractive index. Same way, this glass and this liquid both are having same refractive index. So at that time ANG minus ANL will be what? 0, because both are having same refractive index. So 1 upon FL is equal to 0, or FL is equal to infinite. Means the focal length inside will be infinite, means the lens will be invisible inside.
So we have seen when the lens and the medium in which the lens is placed both are having the same refractive index, so at that time the lens will be invisible. Now our next point is,
In this case, when LNG is greater than ANG, the nature of the lens will change, as LNG minus ANG will give negative. So convex will behave like concave, and concave will behave like a convex lens.
now our next point is how it depends on the radius of curvature. As I said, both are in denominator, so the focal length is directly proportional to the radius of curvature. So directly proportional to radius of curvature only. Now I'm moving to our next topic, that is image formation using convex lens and the concave lens. We have seen in class 10th the 6 cases in the convex lens and the 2 cases in the concave lens. So that's same thing, but only I'm just giving you information about that, nothing new. Starting with the first case, when the object is at infinity. In this case, the object is at infinity and the image is formed at focus or in the focal plane, depending upon the position. If the rays are coming parallel to the principal axis, at that time at focus it will be formed, and if the rays are coming parallel but not at with the parallel to the principal axis, so at that time the image will form in the plane, focal plane. And next is, and the case 2, when the object is beyond 2f, or you can say between infinity and 2f. In this case, when the object is beyond 2f, the image is found between f and 2f. The image is real, inverted and diminished. Case 3, when the object is at 2f. In this case, the object, when object is at 2f, the image is formed at the same position 2f. The height of the image is same as the height of the object. Image is real, inverted, same size of the object. Case 4, when the object is between f and 2f. When the object is in between f and 2f, at that time the image is formed beyond 2f. In this case, the image is a little bit enlarged than the object, but the image is still inverted and real. Case 5, when the object is at focus, at f. At that time, let's see. When the object is at focus, at that time the image formed at infinity is still real, still inverted, but highly enlarged. Case 6, when the object is in between focus and optical center. In this case, the image is formed virtual, not highly enlarged than the object, virtual and erect, as you can see here. So we have seen the 6 cases of image formation using convex lens. Now let's see the image formation for the concave lens. But the problem is it has only 2 cases. One, when the object is at infinity, and the second, when the object is anywhere between infinity and the optical center. So let's see the first case. In this case, as you can see, the object is at infinity and the image is formed at focus. The different thing is the image is virtual, very diminished, you can say highly diminished, and erect. Case 2, and the last case in this case. Let's see, when the object is anywhere between infinity and optical center. In this case, the image is formed between focus and optical center. It is erect, it is virtual in all the cases except the first case. So in this case, again I'm saying image is virtual, erect and smaller, or you can say diminished to the object. So we have seen the image formation of convex and the convex. Now our next topic is linear magnification. As in the case of the mirrors, that definition was the ratio of the size of the image to the size of the object. Same way here also, this is defined as the ratio of size of image to the size of the object. Let's see the proving.
So here is the new topic, the linear magnification by spherical lens. I am taking the convex lens in this case. Here I am taking the object between 2f and f. First ray starting parallel to the principal axis, after reflection goes through focus. Second ray from the optical center and intersects the first ray after 2f, which forms the image here. Let's name it. After naming all, you can say O dash object forms the image II dash beyond 2f. So we are seeing this two triangle OO dash C and II dash C, the two triangle in this triangle. In this triangle, this angle and this angle both are at right angle, means 90, and this angle and this angle are vertically opposite, so they are equal, means performing the similar triangle. Using that property, using two corresponding sides, II dash upon O dash is equals to Ci upon Co. This is same as you have seen in the case of spherical surfaces. It's spherical reflecting surfaces, means you can say in the case of mirrors. So here it is, the definition remains same about the linear magnification, which defines as the ratio of size of image to the size of object. I'm going to prove the same first, taking the object height HO, image height HI, and distance of image V, distance of object U. Let's put all the values here. By the sign convention, the downward distances will be negative, upward distance positive, the right hand side distance positive, left hand side distance negative. And the ratio of image to the object is known as the linear magnification, symbolized by m. Here negative will be cancelled. So final equation. This is the final equation for the linear magnification. Same you can prove using the concave lens.
Now this time to move some numerical for the numerical problem. Some students have some queries in the comment section. So I'm going to solve those questions first. The chapter number, the question number will be written there. So let's see the questions first.
Here we go for the numericals. Chapter 14, question number 3. The question is, a convex mirror produces a real image of half the size of an object. Place 60 centimeter in front of it. Where should be the object be placed to obtain virtual image of double the size of the object? Means first it is producing half size image when it is at 60 centimeter. Now it want to change the position of the object in such a way to get virtual and double size of the image. So starting the word, when the object is placed at 60 centimeter means when u is equal to minus 60, at that time it produces, where is that, half the size of the image, half the size of the object. So since the image is real, so the linear magnification m will be negative and the value is half. So m is equal to minus half. What we will do actually, in both the cases one thing is not being changed, and that is the focal length of the mirror. So we will find first the focal length of the mirror using this case, and we will put the focal length of the mirror in the other case. Means like this, m is equal to minus v by u is the equation and minus 1 by 2 is the value. So what is the relation between v and u? So on putting the value of u, that is minus 60, we will get the value of v here, and let's calculate the focal length first. On putting the value of u and v, means we are getting the focal length minus 20 centimeter, and now we will use this focal length in the other equation, other part of the questions. Let's try going to the next half part of the question. In that question asking where should be the object, so u is equal to question mark. We have calculated the focal length of this mirror, that is minus 20 centimeter. I have written here, and virtual image of double size. So virtual image means positive m and double means 2. So whenever the image is virtual, m will be positive. So using this, now using this equation again, and putting the value, then we will get this. So we get the answer is minus 10 centimeter. I know the book it is given minus 15, that is incorrect. The correct answer is minus 10 centimeter. We can also solve the same question using this equation also. I'm showing you the another way to solve using the value this. See here, in this equation I have put the minus 1 by 2 value of f we are going to calculate using this value. If you will solve further, you will get the same answer, and further now to calculate u, see this, the same answer you will get using this way also. So this is the easiest way, but I have shown you the basic way first, then the standard advanced way. Another question from the comment section, same chapter 14, question number 5. Chapter same, but question number is 5. The question is, an object is placed first at 25 centimeter and then at 40 centimeter from a concave mirror. Means in front of a concave mirror, the position of the object is being changed from 25 to 40. The magnification in the first case is 4 times. The magnification in the first case is 4 times that in the second case. Means in this case the image, suppose the 4 times, in this case only 1 time. And in the second case, the image being real, both cases real means the magnification will be negative, and asking for the focal length. I am going to use the same equation, means advanced method, shortcut method. So when object is at 25 centimeter means u is equal to minus 25 centimeter. Taking m1 is equal to 4n is because first case is 4 times in the second case. Using this equation first, So m1 is equal to 4m f upon f plus 25, making this equation 1. Now next part of the question, when u is equal to minus 40 centimeter, m2 is equal to m, using again the same equation. This time m is the value of m2, f will be same because mirror is same, only position is changing of the object. So now new position is 40. I'm making this equation 2. So I'm dividing equation 1 with equation 2. See what will happen. On dividing, you will see this m will be cancelled. So on further, this will be the new part. So you can see f is cancelled. 4 is going to multiply with this, and this will become on the other side. On doing cross multiplication and cancelling f, you will get this much. 4 f plus 25 is equal to f plus 40. On further solving, and you will get after this f is equals to minus 20 centimeter. That's it. Another query from the chapter 15, question number 16. An equilateral prism of glass whose refractive index is 1.45 is immersed in water whose refractive index is 1.33. An arrow beam of light falls normally on the one face of the prism and find the angle of emergence of the beam. I'll show you using diagram. Here you can see, according to the question, the light falls normally on one face of the prism, which is placed in water whose refractive index is 1.33 and glass refractive index is 1.45. Let's draw further where the ray will go. On producing further, since the prism is equilateral prism, so this will be 60, this will be 90, so this will be 30, the remaining angle is 60. So we found that angle of incidence is 60 and the angle of emergence is we have to find. I'm just naming it as R. So let's change it. Emergence in the question, it is emergence, so I'm making the symbol same. So I'm naming this angle E, means emergence. Let's write first the Snell's law. According to Snell's law, the light is going from glass to water. So G and W sin I by sin R. G and W is not given in the question, nowhere. So we will split it. And I, angle of incidence is given, angle of emergence is we have to find. Let's fill all the values. So A and W, second medium refractive index upon first medium refractive index. Okay. Now sin I is sin 60 and sin R is emergence. Let's fill all the values. On filling all the values, on going further, sin A is equal to 1.732 and into 1.45 divided by 2 into 1.33. Root 3 value is 1.732. On solving that, on solving this, you will get this, or 0.9441. So this is the answer. Angle of emergence is equal to sin inverse this much, or you can calculate the value also, and the angle value is nearly 70 degree. Our next question is from the same chapter, but question number 17 now. A small bulb is placed at the bottom of a tank containing water to a depth of 80 centimeter. What is the area of surface of water through which the light of the bulb can emerge out? For that, I have drawn a diagram for your convenience. See, this is the tanker containing bulb at the bottom, and the light is coming out from every point. But some light, means at least one ray will there, which will go just emerging, and after that total interreflection. So I am taking that ray which is grazing through the surface. How? Just see. So I'm considering the rays are these, after which it is grazing through the surface. After this, the ray will totally interreflect, and before this it will go out of the surface. So this is the area of the surface of water that we are going to calculate. Let the radius of this circle or the disk, or you can say the surface, be R, and the height according to the question in the given 80 centimeter depth. So the height is given 80 centimeter, and since it is grazing, so this will be the critical angle. Let's see, and due to alternate angle property, so this will also be C. Okay, using the critical angle property, as the light is just grazing the surface, so sin C is equal to 1 upon refractive index. So what is the refractive index of water here? 1.33. Let's put that. So sin C is equal to 1.33 or 0.75. So what is the critical angle here? It becomes Sine inverse 0.75. So the critical angle is found 48.5 degree. Now go to the diagram again. See this triangle OAB. In this triangle, we have to find the radius r. We know this length means depth. So if using tan C, we will have perpendicular and base. So I think we can calculate it. Let's use the tan C here. So tan C is equal to AB upon AO. See here, tan C is equal to AB upon AO. Put the value. On putting the value, C is equal to 48.5 degree. So tan C tan 48.5 degree. Radius R and the AO is 80 centimeter. So on putting the value, tan 48.5 is 1.13 R upon 80. So value of R is equal to 90.4 centimeter. This is the value of R, not the surface area. So you can see here the surface area is just a disk. So we can use pi r square equation. Let's find that. So this is in centimeter square, converting into meter square, you will get this much. That is nearly to the 2.6 meters square. One more question was there in the comment. Question next 18 also, but I'm giving you this task in the same way as I have done question 17 using this diagram. You can also solve the question number 18. If not, I will be there.
Here we are completing our
Session.
chapter at this point. The remaining part will be done in
Next
the lab.
class.
And now I'm giving you thanks. And again, if you're facing problem, inform me in the comment section, give me the questions and do solve all the numericals. Till then, thank you.